Welcome viewers to Adisha Tech Tutorial. So in this video we are going to discuss the semiconductor part 1 gate questions. So let's begin. So this question came in EC 2016 for 1 mark. So what it is given here is a small percentage of impurity is added to intrinsic semiconductor at room temperature, that is 300 Kelvin. Which one of the following statement is true for the energy diagram, band diagram shown in the figure? So this is the energy band diagram given. So here you can see in this band diagram the valence band, the conduction band, and one extra energy level, okay, that is which is nearer to the conduction band. So in the theory video we have discussed that the energy level nearer to the conduction band is our ED. Now what is ED? ED is the donor energy level, and how it is found? It is found by adding pentavalent impurity. So when we add pentavalent impurity to intrinsic semiconductor, what we get? We get an N-type semiconductor. So now let's see the options. So here in this option, in the first option it is given that intrinsic semiconductor doped with pentavalent atoms. Yes, it is doped with pentavalent atoms to form N-type semiconductor. Yes, we are forming an N-type semiconductor. So our band diagram is the answer of option A. So here our option A is the answer. No need to further see the other three options. Now let's move on to the next question. So in this question you can see that in an N-type silicon crystal at room temperature, which of the following can have a concentration of 4 into 10 to the power 19? So now let's see the option. So this is a question for EC 2009 for 1 mark. So in the first option it is given silicon atoms. So concentration of silicon atoms, that is the number of silicon atoms per centimeter cube, is how much? It will be equal to 5 into 10 to the power 22 per centimeter cube. So this you have to remember that in silicon crystal your concentration of silicon atoms will be 5 into 10 to the power 22. So it is very much high than 4 into 10 to the power 19. So it is very much higher. So our silicon atom is not our answer. Before going on to the second option, let's move on to the last option, that is option D, that is valence electrons inside the silicon atom. So valence electrons inside the silicon atom is 4. So now what is the concentration of the valence electrons inside the silicon atoms? It is 4 times the concentration of silicon atom, that is 4 into 5 into 10 to the power 22 per centimeter cube. So this is very much greater than 4 into 10 to the power 19. So this is not our answer. Now what is left? Our holes or the dopant atoms. In an N-type silicon, what is dopant atoms? It is the electrons. So it is nothing but concentration of electrons in subscript N, that is concentration of electrons in N-type. So now let's see what is Ni, that is the intrinsic carrier concentration is how much? 1.5 into 10 to the power 10 per centimeter cube, which we have discussed in the theory video. So now in an N-type silicon crystal, your whole concentration, that is Pn, will be less than Ni and Nn will be more than Ni. That is the dopant atoms. So here 1.5 into 10 to the power 10 is very much less than 4 into 10 to the power 19. So holes is more less than 1.5 into 10 to the power 10. So our holes is also not our answer. So what is left? The dopant atoms is our answer. How? Your Nn is greater than 1.5 into 10 to the power 10. We should be nearer to 4 into 10 to the power 19. So our option C is correct. That is dopant atoms are the concentration of electrons inside N-type silicon crystal. Now next, moving on to the third question. So here you can see that a bar of gallium arsenide. Okay, so what is gallium valency? Gallium is a trivalent, so it is having a valency of 3, and arsenic is a pentavalent atom, it is having a valency of 5 is doped with silicon. So when these two are doped with silicon, tri and penta, then what we get? We get a compound semiconductor. So we are getting a compound semiconductor such that silicon atoms occupy gallium sites and arsenic sites in the gallium arsenide crystal. So here we will make two columns, one for gallium sites and another for silicon sites, arsenic sites. So gallium, arsenic. So when your silicon occupy gallium sites, what we will get? When silicon will occupy gallium sites, we will get arsenic impurity with silicon. So pentavalent impurity with silicon give rise to N-type semiconductor. Now when your silicon takes arsenic sites, what we will get? A trivalent impurity with silicon. So it is having 3. So we will get a P-type semiconductor. Now let's see the options. So silicon atom act as P-type. So this is a P-type. In arsenic sites, yes. So silicon atom is acting P-type in arsenic sites. It's correct. And N-type dopants in gallium sites. So it is acting N-type dopants in gallium sites. So our option A is correct. So you need to form a column so that it becomes easier to visualize the option and we will not make any mistake. So no need to see further option. So our option A is our correct answer. Now in this question it is given, it is EC 2003 for 1 mark. It's given that intrinsic carrier concentration of silicon sample at 300 Kelvin is 1.5 into 10 power 16. So Ni is given here, which will be equal to 1.5 into 10 to the power 16 per meter cube. If after doping the number of majority carriers is 5 into 10 to the power 20, the minority carrier density is how much? So here majority is given 5 into 10 to the power 20 per meter cube. So the given values are in meter cube and the options are also in meter cube. So no need to change into centimeter cube. So what do you mean by majority and minority carrier inside the semiconductor? So for P type and N type, the majority carriers are holes here and the majority in N type is electrons and the minority in P type is electrons and the majority is holes. So it is written as subscript P, it is also written as for P type subscript P and for N type it is subscript N. So we have a common formula for both, that is minority carrier will be equal to Ni square divided by the majority carrier. So this is a common formula for both the types of semiconductors. So here it is given the majority is 5 into 10 to the power 10. We need to find the minority. So we will substitute Ni. It is given that 1.5 into 10 to the power 16 divided whole square divided by how much? 5 into 10 to the power 20. So now it is 2.25. So 1.5 square is 2.25 into 10 to the power 32. So 10 to the power 16 square is 10 to the power 32. So it is 5 into 10 to the power 20. So after simplification we will get its value as 4.5 into 10 to the power 11 per meter cube. So option A is our answer. Now next moving on to the question. So here this is an easy question, came in 2005 for 1 mark. So now again we have to substitute the previous formula here. So the minority carrier in an extrinsic semiconductor and under equilibrium is what? So here we know that minority is equal to Ni square divided by majority. So this is the formula which we have to compare with the options. So here it is directly proportional to the doping concentration. The minority is directly proportional. No, this is not our answer. So inversely proportional to the doping concentration, yes, it is inversely proportional to the doping concentration. Doping concentration is what? It is the majority concentration. So our minority is inversely proportional to the doping concentration, that is the majority concentration. So option B is our correct answer. No need to see the further options. So the electron and hole concentration in an intrinsic semiconductor is given as Ni. So it is nothing but the intrinsic concentration, which is Ni per centimeter cube. It's given at room temperature. Now if acceptor impurities are introduced with a concentration of Na per centimeter cube, so here acceptor impurity is given as Na per centimeter cube. Acceptor is added, acceptor atom, so it is a p-type semiconductor. The electron concentration at 300 Kelvin. So for p-type, what is electron concentration? It is Np, that is equal to Ni square divided by Na, that is the acceptor atom concentration, or we can say it as the hole concentration. Okay, so Np is nothing but Ni square divided by Na. So here your electron concentration is Ni square divided by Na. So option D is our correct answer. So this question came in 2014 for 1 mark. So it's given that silicon bar is doped with donor impurities Nd. So we are considering donor impurities, means the semiconductor is N-type, which is 2.25 into 10 to the power 15. Given the intrinsic carrier concentration Ni, which is 1.5 into 10 to the power 10. So for N-type semiconductor, your electron concentration, that is Nn, will be how much? It will be equal to Nd. But here it is given that we have to assume complete impurity ionization. What do you mean by impurity ionization? It is equal to alpha times of Nd. So here we have to consider an ionized donor concentration, that is Nd plus, and which will be equal to the impurity ionization alpha into Nd. Here it is given complete impurity ionization, so your alpha will be equal to 1. So our Nn value it will be equal to Nd. So Nd value is given how much? 2.25 into 10 to the power 15 atoms per centimeter cube. So let's first see the options. What is the value of N? So in the first option it is 1.5 into 10 power 16, so it is not our answer. In the second option it is again 1.5, so it is also not our answer. In option C it is 2.25 into 10 power 15. In option D also it is the same one. So our answer is either C or D. So for that we need to calculate what is the value of P. So for calculating P we need Ni intrinsic concentration, that is equal to 1.5 into 10 to the power 10 per centimeter cube. So to calculate Pn now, we have to write down the formula. Pn is equal to Ni square divided by the electron concentration, which is equal to Nd. So we can write directly Nd. So now we can substitute the values, that is 1.5 into 10 to the power 10 whole square divided by Nd, which is 2.25 into 10 to the power 15. So 1.5 square is 2.25 and 10 to the power 10 square is 10 to the power 20 divided by 2.25 into 10 to the power 15. So by simplification what we will get? We will get 1 into 10 to the power 5 per centimeter cube, which is our answer, this. So our answer is option D. Okay, so if impurity ionization is given, we need to consider your electron or hole concentration as Nd plus or Na plus, which is nothing but the impurity ionization times of Nd. So according to the value of alpha, we need to calculate our Nn or Pn according to the types of semiconductors. Now moving on to the last question. So in this question it is given that silicon sample is doped with Nd. So when silicon sample is doped with Nd, whose value is 1 into 10 to the power 15, what we get? We are adding donor impurity, so we will get an N-type semiconductor. Now next it says that assuming the intrinsic carrier concentration Ni, which is 1.5 into 10 to the power 10. Now in the third part it says if the sample is additionally doped with Na, which is equal to 1 into 10 to the power 18 per centimeter cube. So here again it is doped with Na, which is equal to 1 into 10 to the power 18 per centimeter cube. So after adding your acceptor impurities, what you are going to get? You are going to get a p-type semiconductor on a whole. So on a whole you will get a p-type semiconductor. Why? Because your acceptor impurity Na is greater than Nd. How it is greater? Because it is having a degree of 10 to the power 3 more than your Nd. So now what we need to calculate? We need to calculate the electron concentration. So for p-type we need to calculate the electron concentration. So how we will calculate? So here your Np will be equal to electron concentration in p-type will be how much? Ni square divided by which impurity? Which impurity atom? It will be equal to the subtracted form of Na minus of Nd, because Na is more here. So Na minus of Nd will be your concentration of doping atoms. So we can substitute the value of Na, given value of Na, which is 1.5 into 10 to the power 10 whole square divided by how much? Na minus of Nd. So to subtract this, we need to make the power of degrees same. So here it is 1 into, so for Na we can write in terms of 10 to the power 15 power. So it will become 1000 into 10 to the power 15 minus 1 into 10 to the power 15, the donor impurity. So here by simplification we will get 2.25 into 10 to the power 20 divided by how much? We can take 10 to the power 15 common. So we can take 10 to the power 15 common into 1000 minus 1, that is 999. So by calculation we can get as the answer is 225. It will be approximately equal to 225 per centimeter cube. So this is our electrons concentration inside the p-type semiconductor. So that's it for the semiconductor part 1 gate questions. In the next video we will be discussing semiconductor part 2 theory portion. So stay tuned for my next video. Take care. Goodbye.